This lecture is about binding energy, which is a little bit like negative potential energy. When we try to bring two deuterium nuclei together, that is very difficult. As we know, nuclei are positively charged, so they repel each other based on the Coulomb force. And the problem with the Coulomb force is that it gets stronger the closer the nuclei come together. We know that the Coulomb force falls off as 1 over the distance squared. However, once we manage to bring those nuclei so close together that they touch, they may actually fuse together, and in this case the two deuterium nuclei may form a helium-4 nucleus. The reason for this is what we call the strong nuclear force, which acts between protons and neutrons and between protons and neutrons, as opposed to the Coulomb force, which only acts between charged particles such as protons. Now the thing is that the strong nuclear force is much stronger than the Coulomb force, but only over very short distances, which is why we have to bring the nuclei very close together before the strong force overcomes the Coulomb repulsion and nuclei can fuse together. What allows us to build helium atoms. Also, in particular, the much larger nuclei. And we therefore also need the neutrons, because if we were trying to form a large nucleus with only protons, then soon the distance between the protons would be so large that the Coulomb repulsion would simply make the thing fly apart. So what the neutrons do is two things. They increase the average distance between the protons, and they add in more of the strong nuclear force, which sort of acts like a glue to keep the nucleus together. So let us now try and calculate this binding energy by looking at a carbon nucleus, which has a mass of 12.00 atomic mass units, 12.0 U, and compare this to the mass of its constituents. So the mass of a neutron is 1.0087 U, and that of a proton is 1.0073 U. So what we then see is that the mass of a carbon nucleus is actually smaller than the combined mass of 6 protons and 6 neutrons. So the sum of the mass of 6 protons and 6 neutrons is 12.096 U. If you want to bind this together into a carbon nucleus, bring them close enough together, the mass reduces, and then we know from Einstein's E equals to mc squared that energy must be released, and the energy is then exactly this amount, 0.096 U times the speed of light squared. Equivalently, if you want to break apart a carbon nucleus into its constituent protons and neutrons, we have to add energy in. And the sum of the mass of the protons and the neutrons is 0.096 U times c squared, larger than the mass of the nucleus. So this is the amount of energy that we have to put in to get the protons and neutrons back. And this is the definition of the binding energy. What is the amount of energy that we have to put into a nucleus to break it up into its constituent protons and neutrons? So the difference in mass between the mass of 6 protons and 6 neutrons and the mass of a carbon nucleus, 0.096 U, is called the mass defect of a carbon nucleus. It's sort of the mass that is not there, the absent mass. Equivalently, the binding energy is the same amount, 0.096 U times c squared is 92 MeV, and this is called the binding energy, which is the energy we have to put into the nucleus to break it up into protons and neutrons. So by Einstein's equation, the binding energy is equivalent to the mass defect times the speed of light squared. So here we see a list of elements of different nuclides. Deuterium is hydrogen 2, and for each of them we have the nuclear mass, and by knowing the number of protons and neutrons protons, we can also calculate the mass of the nucleons, and hence the mass defect and equivalently the binding energy. And since we know the number of nucleons, we can also determine the binding energy per nucleon, which is a measure for the stability of a nuclide. And what we see here is that there is a sort of maximum around iron 56, so that's among the most stable nuclides. What we can also see in this table is that helium-4 has a relatively high binding energy per nucleon amongst the lower mass nuclei. And this is the reason that stars, after they fuse hydrogen into helium, they don't go on to form lithium or boron or beryllium, but they jump over to carbon, which is the next more stable atom in the periodic table. So here we see a schematic of the binding energy per nucleon for a number of nuclides, and there is a sort of peak around iron 56. So the nuclides there have the highest binding energy per nucleon, and therefore they are the very stable nuclides, so particularly iron and some nuclides of nickel. To the left, we find atoms with lower nucleon numbers and also lower binding energy per nucleon. So what this means is that if we take some of these smaller nucleons and fuse them together, they can form more stable nucleons. On the right hand side, again, the binding energy per nucleon is less than that of iron. So what may happen is that heavy nuclei may spontaneously decay or fission, break into smaller parts to turn into more stable nuclides.